So we're going to begin our first actual Algebra 2 unit with a application. It's an application of actually quite a few algebra skills. It puts them all together, and the process that we're going to study is called linear programming. Now, linear programming, as you're going to discover, has as its goal to find the optimal value of a collection of given facts, a collection of given restrictions, and when we put all this together, we will end up with what, so to speak, is the best answer. Now, what we're going to do is sample one, and we will end up doing it on your little sort of graphic organizer. We actually use this graphic organizer for every problem that we do for the next few days. But look at example one with me. It has to do with telephones. We've got two different styles of telephones. One of those styles is deluxe, and one of them is standard. Now, it says that each deluxe phone gives you $9 in profit. Each standard phone gives you $8 in profit. I know, it's not a whole lot of profit. Maybe these are just like toy phones. But in any case, we've got two machines that make these phones. Now, a deluxe phone is going to require 3 hours of machine A time, but also 1 hour of machine B time. So maybe these two machines do different things to make a deluxe phone. And then we've got the same thing with a standard phone. Well, we've got the fact that a standard phone requires 2 hours of machine A, but also 2 hours of machine B. So it's a different sort of mix of machine time. So what we want to do is, well, not what we want to do, but we realize that there's 12 hours available on machine A and machine B combined. 12 hours on machine A, but 8 hours on machine B. Now, that's a lot of information. Now you get the idea of what I mean by putting this all together so that we can end up with well, the most effective, as it says here, to generate the most effective profit for the company. In other words, we want to get the most profit. So let's begin the process of linear programming. And as with any application problem, your first step is going to be to define the variables. Now we're talking about the variables of X and Y, which are often the things that are unknown. You might feel like there's a lot that's unknown, but if you think about it, it has to do with the phones, specifically how many phones. So let's say that X is going to be how many deluxe phones. We don't know how many deluxe phones, but that's what we're going to try to find. And then how about how many standard phones for the Y? So when we say how many, we don't mean the cost, we don't mean the color, but we literally mean how many of each of those phones. Now, if you're saying, well, just make as many as you can, that's exactly what we're going to try to do. Just the only problem is we got to make sure we stay within the constraints of the problem. Now, the objective quantity, that's a new word, but the objective quantity ends up being an equation. It ends up being an equation for that which you're trying to find. And if you read carefully again here, it says we're trying to find profit. So really, our objective quantity is going to be the profit that we make. Now, except that we want to turn that into an equation, and now we got to start getting into the numbers. Now, if you go back and read, it says that you get so much profit from each phone. Remember, it was in the first few sentences up here. You get $9 profit. You get $6 profit for each kind of phone. We're going to take those two numbers. We're going to use them. Somebody's banging on the wall as I try to record this. But we're going to use $9 profit for every X and $6 profit for every Y as our equation. Okay, now, before we go any further, please understand We don't know how many phones we need to make. Okay, but if we knew how many phones we made, then we would know what our profit is, because our profit's going to be $9 for every X phone and $6 for every Y. And that's what this problem's all about, trying to figure out how many phones we're allowed to make. Okay, and it's all based on the constraints. The constraints, you're going to find out, are like a system of inequalities. Now, a system of inequalities is fancy talk for statements that involve greater than or maybe less than. Now, unless otherwise stated, all linear programming problems will contain what's called an assumed constraint. Assumed that X and Y cannot be negative. And since they can't be negative, we'll say that they have to be greater than or equal to 0. All this is saying is that we're not going to have any negative phones. All right? I hope that they get chiseled off that wall what they need soon. So we're not going to have any negative phones. Now, the other two constraints get a little more complicated. But if we go back and read carefully, we find out that there's statements about machine A and machine B. And those statements about machine A and machine B refer to how many hours they can work. In the middle of your paragraph, it says that a deluxe phone is going to require 3 hours of machine A. But it says that a standard phone is going to require 2 hours of machine A. Do you see how 3 hours and 2 hours, 3 hours for every X phone, 2 hours for every Y phone, are going to be required, but I can't go greater than, so that means I have to be less than the total amount of hours available for machine A. And again, that is 12. I wonder if you can write the constraints for machine B. Yes, I'm going to write it down in a second, but it would be even better if you try to write it down. Let's go back to the sentence. It says 1 hour for machine B, and it says 2 hours for machine B. And of course, that's for each type of phone. So 1 hour for every X phone, 2 hours for every Y phone. And that can't be greater than 8. Why can't it be greater than 8? That's the amount of hours available for machine B. Now, this indeed is getting a little more complicated, but the truth is these constraints can be visualized as a graph. And when you graph those constraints, you'll be able to see what usable numbers we have for this phone problem. So let's graph the first equation. Now I'm going to put that first equation, I'm going to highlight that first equation in yellow. And I'm going to remind you guys that when you graph an equation in standard form, it's very nice to use X and Y intercepts. And so if we're going to use X and Y intercepts, we could plug in to that equation. We could plug in 0. Now, when you plug in 0 for X, you get the Y intercept. Somebody says, what'd you do with the less than sign? It's just an equal sign. Well, remember, what we're trying to do is we're trying to find the points on the line, and points on a line are always, lines are always described by equal signs. So a little bit of simple math, and we get Y equals 6. Now you want to understand that Y equals 6 is the Y intercept of our yellow highlighted graph up here, or equation. I think we could probably plot that point right now. 1, 2, 3, 4, 5, 6, and perhaps even label it so we don't lose track. Don't we also need the Y intercept? Yes, we do. The Y intercept is found by, we just found the Y intercept. Don't we now need the X intercept? Yes, we do. The X intercept is found by plugging a 0 in for Y. And if you plug a 0 in for y, just make sure I show it here, we get a nice little equation that 3x equals 12. We'll divide that by 3 so that we can solve it, and now you have your x-intercept. Now, remember, we talked about this about a week ago. I'm just simply reminding you that an easy way to graph 1, 2, 3, 4, an easy way to graph an equation of this form is by using the X and Y intercepts. Now we call that the boundary line, but remember that this was a less than problem. It was less than 12. So what we need to do now is we need to use a test point to be able to see where you actually want to shade. Now when you use a test point, you do want to go back to the original inequality. What I mean is you actually want to go back to the less than sign. Notice that I plugged in 0 and 0 as my test point. That way I know for sure if it comes out true or false. And so when I plug in 0, I get the statement 0 is less than or equal to 12. That is definitely true, and that means that the test point of 0, 0 is part of my shaded region. So what I'm going to do is I'm going to shade this in. Let me shade it in with something that looks a little bit better. We'll shade it in like this. How about the second equation? Do you think you can graph that using the X and Y intercepts? How's that going for you? Graph that using the X and Y intercepts. If you plug in a 0 for X, you kind of get that one to disappear, or it just becomes 0. Might be a little bit better. That means 2y equals 8, so y equals 2. So you can graph y equals 2. Excuse me, that's not good math. I'm going too fast. If I divide this by 2, I think y equals 4. So y equals 4 would be my y-intercept for that second one. And then if I plug a 0 in for y, that'll become 0, and I'll just get x equals 8. And x equals 8 is going to be your x-intercept for that second one. Okay, and again, you actually are drawing that boundary line, and that boundary line is needs to be through the points a little bit better. There we go. But that boundary line actually creates my second space for that graph, for that equation. Now I want to use a test point. I can plug in, let me make sure I show this. I can plug in 0, 0 again. It's a good test point. I'm going to be plugging that in for x right there and for y right there. And we're trying to see if that's less than 8. Now the nice thing about plugging in 0, 0, the nice thing about plugging in the test point 0, 0 is that it makes all of your equation equal 0. And is 0 less than 8? Indeed it is. Now remember, because that's a true statement, that means that we're going to shade on the test point side. So we actually end up shading on this side of that boundary line. Now, you might say you didn't do anything with your first two constraints. You didn't shade those. Well, actually I did, because if x and y have to be greater than 0, that just means that I'm only going to be using positive numbers. This entire graph is using the positive numbers. So yes, we did already graph that because we're only using this corner of our graph. Now, do you understand that the shaded region, or I should say the common shaded region, is actually the region that contains the usable combinations of phones? And I'm trying to highlight it now a little bit more in blue, or perhaps I will get rid of the other regions that are highlighted here. Again, I want you to understand that the region that's highlighted in blue is our common shaded region. And that means that the only points that are in that region are the ones that I can use for this phone problem. But if I want to get the most amount of money, I then will only be required to use the vertices. And the vertices I'm highlighting in red end up being these 4 points. Tell you what, let's highlight them in blue. That actually would stand out a little bit better. So the vertices, which are the points that are kind of at the edge of this graph, are the only ones that could ever give me my highest profit, again, simply because they are the biggest ones. Now, it looks like 0, 4 is a vertice. It looks like 4, 0 is a vertice. Now, technically, 0, 0 is a vertice because it's at the edge of the graph, although it doesn't take long for students to say that there's no way that that's going to give us our maximum profit. It's certainly the smallest number, but it technically is a vertice. There's one more. It's this point that's kind of in the middle, isn't it? It's this point at 2, 3. And 2, 3 is another point that's on the edge of my graph that technically, not technically, but that is a vertice that I'll be able to use in my final computation. Now, understand that these 3 points, 1, 2, 3, actually represent combinations of phones. The question is, which combination is the one that's going to give me the most profit? Well, remember, profit comes from 9x plus 6y. And now that I know what my x and y's are, I can plug into that profit equation. I'll plug in 1 by 1. I don't want that line there. I'll plug in 1 by 1. So let's do the first one. So $9 for, here, let me organize this a little bit better. The first one that we're doing is the point 0, 4, which really means 0 deluxe phones, but 4 standard phones. So if we plug in 0 deluxe and 4 standard, we end up with 0 plus 24, $24. Woohoo! That's your profit if you make just 4 standard phones. What if I make 4 deluxe phones? Well, it's $9 for every deluxe. I'm not going to have any, let's get the colors right here. I'm not going to have any, sorry about that. I'm not going to have any standard phones. I'm getting ahead of myself. So we have 4 deluxe phones, no standard phones. Looks like $9 times 4 phones plus 0 is $36 profit. Woohoo! Even more. What if I make a little bit of each? And it turns out that if I make 2 deluxe phones and 3 standard phones, I'm going to get 18 plus 18, which is also 36. Now, if you're kind of wondering, what is it that we're trying to do? What really is the final answer to this problem? The final answer was to find the combination of phones. And do you understand that that combination has now been discovered because these 2 combinations both give me the largest profit? We just need to say so. We need to make like a little statement. And this statement might sound something like this. You can make 2 deluxe. You can make 2 deluxe and 3 standard. Or you could make 4 deluxe and 0 standard. Yes, you could just make all deluxe. So that's your combination of phones, and that'll give you a max profit. I'll give you a max profit of $36. So let's review the steps to this problem. First thing we did was we honestly read the problem, After we read it, we realized what it was we were trying to do. We were trying to determine the mix of phones that will give us the greatest profit. So the mix of phones, that is the how many phones, is your X and Y. And then we have this objective quantity, which will always be profit, because that's what you're trying to optimize. You're trying to get the most money. You had to write some constraints. Those constraints come from reading the paragraph and understanding what's greater than or less than. Once you get those constraints, you go to the task of graphing them. Now, graphing constraints is ultimately a job of trying to graph lines which make a shaded region. That shaded region will have vertices. The vertices are going to be the furthest tips on that shaded region. It looks like that those three, although there was a fourth vertice, those three vertices are the ones that we can use to check the profit. And we basically plug them in one at a time. We find out that we had a tie, $36 profit, and that happened two different ways, and you make a little statement to say so. Now, what I want you to do, and this is partially for homework, is to try to set up the variables, the objective quantity, and the constraints for this lumber problem. Again, all I want you to do is set it up. So what you're going to be doing is step 1, which kind of has 2 parts to it, and step 2. Okay, now, if you think you're right, you can continue with the rest of the problem. But again, as homework, I'm only asking you to do step 1 and step 2, because what we will do is we will continue with the problem tomorrow. Okay, we'll basically finish the problem.